Another important property we need to talk about are some properties on triangles. The first graphic that I have listed here is just basically giving you how we can classify triangles. We can classify triangles either by their angles or by their sides. So if I want to classify or discuss triangles by their angles, I have here an acute triangle where we're talking about all of these angles being less than 90. I have a right triangle here where one of the angles in the triangle is equal to 90 degrees, making these other two angles acute. Now, right triangles are extremely important and we utilize them extensively in trig. Finally, we have an obtuse triangle where one of the angles is greater than 90, which leaves these other two angles as being acute. Additionally, if I don't want to classify my triangle, say, by angles, I can classify it by sides. Here I have an equilateral triangle where all of the sides would be equal. I have an isosceles triangle where two of the sides would be equal, and a scalene triangle where no sides would be equal. So let's take that and let's expand that understanding of triangles into what we call similar triangles. Now, similar triangles are defined in the following way. Similar triangles have corresponding angles that have the same measure. So by definition, if I have similar triangles, their angles are the same measure. So you can see here I have two triangles that are obviously not the same size, but if I knew that they were similar, then I would be able to say, well, because they're similar triangles, these angles here at the top of my triangle are going to be the same measurement. Just like these angles here, this angle here across from the hypotenuse of the big triangle would have the same measure as this angle across from the hypotenuse of the smaller triangle. So we can use the definition of similar triangles while discussing angle measurements. We can also use the definition of similar triangles when we talk about sides. So again, by definition, similar triangles have corresponding sides that are proportional. Now remember that a proportion is basically two ratios that are set equal to each other. And I'll show you what I mean in just a minute, but the way that we're discussing this is basically saying this side CA of the large triangle corresponds with this side ED of the smaller triangle. Now obviously these two measurements are not the same value, but they differ by a factor of 2. So we're going to use that concept to be able to solve this next example. So this example wants us to be able to determine these given sides of the smaller triangle if I know already that these are similar triangles. So I'm going to use my definition of similar triangles to be able to solve for the missing sides. So we're going to start out with side A. So side A, when I use the corresponding sides, which is the definition of similar triangles, I look at the side of the large triangle and its corresponding side of the small triangle, and I can set them up as a ratio of big triangle side to little triangle side. So that looks like 12 centimeters over 6 centimeters. And because I'm doing big triangle over little triangle, I'm going to come over here and I have to do it exactly in that same order. Big triangle side over little triangle side. So I have big triangle side over little triangle side, which is the value that I am trying to solve for. So you can see I have a proportion here, which is going to allow me to cross multiply and solve for A. Now the only key to this is that I had to start with one of the fractions in my proportion had to have all known quantities. So I just started with one side that was a big to little that I knew I had known amounts for, and I filled in the corresponding sides for the big triangle and the little triangle. Now we're going to cross multiply and I get 12A is equal to 6 times 12, which is 72. Divide both sides by 12 and I find out that side A is equal to 6 centimeters. So I have 6 centimeters over here. Let's do that again, only now let's talk about side B. So as long as we're using the definition of similar triangles and setting up proportions, then it really doesn't matter how I set up my proportion as long as I'm consistent in what I'm comparing. So this time let's compare all big sides to all little sides. So I've got to have all big sides to all little sides. Now because I have to have known values in my first fraction, and my little fraction over here deals with the hypotenuse and this leg up here, those sides correspond with the hypotenuse of the big triangle and again this leg over here. So what I'm going to do is I'm going to set up a ratio of all big side to big side, which looks like 12 centimeters over 14 centimeters, which is equal to little corresponding side over little corresponding side. So as long as I set it up as big triangle to big triangle equals little triangle to little triangle with their corresponding sides, I'm going to solve this and get it works out exactly the same. So I'm going to cross multiply again, and I get 12b is equal to 14 times 6, which is 84. Divide both sides by 12, and I find out that b is equal to 7. And that is consistent with what we would consider here. I know that these two triangles look to be differing, or their sides are different by a factor of 2. So if I multiplied 6 by 2, I get 12. Again, 6 by 2, I get 12. And just checking, 7 by 2, I get 14. So that's how we would solve it using similar triangles. It doesn't matter, again, if I go from big triangle to little, big to little, as long as what I'm comparing in the first fraction is in the same order as what I'm comparing in the second fraction. Okay, let's expand that just a little bit further, and let's look at this example right here. Okay, this is actually an interesting problem, because what we are going to be able to do is use corresponding triangles to figure out what the height of this tree is based on this person's height and their shadow. So I know that the height and the shadow create a triangle, along with the height of the tree and the tree's shadow, which create a triangle. And because of that, I can say that these are going to have similar angles, because the sun coming down would produce the same angle for the shadow. So that's how come I can say that these two are similar. Additionally, I know that the person and the tree are both perpendicular. Their heights are perpendicular to the ground, so I can come up with similar triangles that way. So if I wanted to set up a proportion of this, I do it similar to the example we just worked, where I'm trying to find the height of the tree. So I'm going to use the shadow of the boy to the shadow of the tree. So I've got 42 inches over 38 feet is equal to the height of the boy to the height of the tree. 63 inches over the height of the tree. Now notice that I'm not in the same units here. I'm in inches for the boy, and I'm in feet for the tree. But that doesn't matter. I don't have to have the same units as long as what I'm comparing is inches to feet, inches to feet. Okay, so now we're going to cross multiply, and I have 42x is equal to 63 times 38, which is 239. Divide both sides by 42, and I find out that the height of the tree is 57 feet tall. Okay, so using the idea of similar triangles and just the height and the shadow, I'm able to figure out what the height of the tree is.